What if your incoming winter air was already 48 degrees warmer than the outside temperature before it even reached your furnace? What if that warming happened without a single watt of electricity, without a compressor, without any fuel burn at all? What if this wasn't a prototype but a method quietly heating farmhouses across North Dakota, interior Alberta, and northern Maine right now? And what if the entire system could be built for less than $300 using materials you could pick up in a single pickup truck trip to any home improvement store? Because that's exactly what's happening. And the physics behind it has been published in engineering textbooks since 1932. Here's the setup most homeowners don't realize they're trapped inside. Every winter, your heating system has to take outside air that might be negative 10 degrees Fahrenheit and warm it all the way up to a livable 68. That temperature climb is where most of your fuel burns. The heating system isn't just maintaining comfort, it's fighting the cold air that keeps leaking in through every crack, vent, and weak point in your building envelope. A large chunk of your monthly heating bill, often 40 to 60% in cold climates, goes toward reheating that infiltrated air. If there were a way to feed your furnace with air that's already halfway to room temperature, your fuel costs would collapse. There is. It's called an earth tunnel, tuned specifically for winter heating, and it's one of the most underused pieces of applied physics in modern home design. Get this. The ground beneath your feet, starting at around 6 feet deep, maintains a temperature somewhere between 46 and 54 degrees Fahrenheit across most of the northern United States and southern Canada, even when the surface is buried under 3 feet of snow. And the air is snapping trees with cold. The soil below the frost line doesn't care. It sits there, stubborn, stable, year after year. That stability is a heating resource most people never think of. If you pull outside winter air through a long buried pipe before it enters your home, the soil transfers its warmth into the air. Negative 10 goes in, plus 43 comes out. Every time. Now let's do the honest financial math. A typical 2,000 square foot home in a cold climate spends between $1,800 and $3,200 a year on winter heating alone, depending on fuel source and local rates. Propane is the worst. Electricity runs close behind. Natural gas is cheaper, but still a chunk of the household budget. Multiply that across a decade. Most of that money is going to warm air that the ground was already willing to warm for free. The earth tunnel doesn't replace your furnace, it unloads your furnace. A heating system that used to run 18 hours a day now runs maybe 5. Your fuel use drops by 50 to 70%. Your furnace lasts longer because it's not working as hard. Your pocket refills. This is the part where people start asking the natural question. If it works this well, why isn't it already standard? The honest answer has nothing to do with secrecy. It has everything to do with who profits from your heating bill. Utility companies profit from high winter consumption. Fuel suppliers profit from recurring deliveries. HVAC contractors profit from installation and servicing of expensive equipment. A buried pipe that preconditions your air threads none of those needles. Nobody makes money off it after day one. So the technology gets quietly filed under things we don't promote. And the next generation of homeowners grows up never hearing about it. The roots of this idea run deep. In northern China, around 200 BCE, rural builders were already burying long clay pipes beneath their courtyards to deliver tempered air to sleeping quarters. Archaeological excavations at sites in Shaanxi province have turned up multi-hundred-foot runs of fired terracotta pipe sections, carefully fitted, clearly designed for air movement. Norwegian farmhouses from the 1600s used what was called the stovepipe system, a stone-lined earth channel that drew air from a distant hillside into the home's central stove cavity. Inuit traditional architecture, perfected over thousands of years in the Arctic, used a long entry tunnel called a katak that ran below snow level to warm incoming air before it reached the living space. Same principle, different materials. Same physics. The modern Western record picks up in the early 20th century. A German agricultural engineer named Konrad Steinberg published a detailed article in 1932 in the journal Landwirtschaftliche Beforschung titled Erdwärmeregister im Winterinsatz, which translates to Earth Heat Registers for Winter Use. Steinberg measured systems on 37 rural farmhouses in Bavaria across 2 winters. His conclusion was unambiguous. Properly sized earth channels reduced winter fuel use by an average of 54% with no mechanical assistance at all. His findings went largely ignored during the war years and the cheap oil decades that followed. They were rediscovered in the 1970s when fuel prices spiked, then forgotten again when prices collapsed in the 1980s. In North America, a handful of owner-builders kept the idea alive. Mother Earth News published a winter-focused EarthTube article in their December 1981 issue. A Canadian homesteading quarterly called Harrowsmith ran a similar feature in February 1984, focused specifically on prairie winter installations. The University of Minnesota's Agricultural Engineering Department tested a commercial-scale EarthTube system at their Crookston Research Station between 1987 and 1991. Their published results confirmed Steinberg's findings almost exactly. The data is public. The designs are public. The results are boringly consistent. What changed between 1991 and now is the cost of fuel. In 1991, the national average residential heating oil price was about 90 cents per gallon. Propane was around 1.10 per gallon. At those prices, even a 50% reduction in fuel use barely moved the needle on the household budget. EarthTubes made sense for homesteaders and researchers, but they didn't have broad financial appeal. Today, residential propane runs between $3.00 and $4.50 per gallon depending on region. Heating oil runs similar. A 50% reduction in fuel use today saves a real household real money, often more than $1,200 per winter. The technology didn't get better. The economics got dramatically more favorable. And the math is only getting stronger as fuel prices trend upward year after year. There's another historical thread that rarely gets discussed. In post-war East Germany, under the severe fuel rationing of the 1950s and early 1960s, rural builders were officially encouraged to install what they called Erdluft-Vorwärmer, or earth-air preheaters, as part of any new farmhouse construction. State archives in Dresden list more than 3,400 documented installations across the GDR between 1954 and 1968. Many of those systems are still operating today, more than 60 years later, with nothing more than intake screen cleaning along the way. The Germans, East and West, have quietly produced the single largest real-world dataset on these systems, and the results are uniformly positive. Time to look at the nuts and bolts of a winter-optimized build, because this is where most people discover how doable it actually is. The core of the system is a single length of pipe, or sometimes two parallel pipes, buried below the frost line. In most of the northern tier of the continent, that means at least 8 feet of cover over the pipe. In severe climates like interior Alaska or Manitoba, 10 to 12 feet is safer. The pipe diameter for winter heating is typically slightly larger than for summer cooling. 6 inches is the common choice. The length runs between 80 and 150 feet. Longer runs extract more heat from the soil, which matters more in deep winter. The pipe material is the one place where corners absolutely cannot be cut. Use smooth-walled Schedule 40 PVC or HDPE. Corrugated pipe traps moisture and dust. Metal pipes corrode. PVC lasts indefinitely underground and is what the overwhelming majority of modern installations use. The intake end rises above ground level and gets capped with a screen, a rain hood, and ideally, a small plenum that lets you inspect for debris. The intake should be at least 18 inches above the maximum expected snow depth for your region. The outlet end enters the home through a basement wall or a ground floor mechanical closet. If you have a furnace, the EarthTube feeds preconditioned air directly into the return side of the furnace, letting the furnace finish the warming. If you have a wood stove or a radiant heating system, the tube can feed a dedicated fresh air register. A small inline duct fan, drawing between 30 and 60 watts when running, pulls the air through the tube at a controlled rate. That fan is the only electrical component. At 40 watts average draw running 12 hours a day, it uses about 175 kilowatt-hours per year. Total annual electrical cost for the fan is typically between $22 and $35 depending on local rates. That's your only running expense. Here's the material cost breakdown for a DIY build. About 150 feet of 6-inch Schedule 40 PVC pipe, around $140. Pipe fittings, end caps, and cleanout tees, $35. Intake hood and insect screen assembly, $28. A quality inline duct fan rated for continuous use, $75. Miscellaneous hardware, mounting brackets, and sealing tape, $22. Total, $300, give or take. That's the number that makes this a realistic project for ordinary households. Now the honest part. Labor on a winter-optimized install is significant. Digging a 150-foot trench 8 to 10 feet deep isn't a hand shovel job. Renting a mini excavator for a day runs between $275 and $425 in most regions. Hiring an excavation contractor for a one-day trench runs between $1,100 and $1,900. If your soil is rocky or contains heavy clay or existing root systems, expect the higher end. Plan the excavation for late summer or early fall when the ground is workable and you have time to backfill before frost sets in. Let me hand you 3 working systems because this is where skepticism dies. Thomas Nielsen homesteads 44 acres in western North Dakota. Winter lows in his area routinely hit -25 Fahrenheit. He installed a dual-pipe earth tunnel system in 2014, 2 parallel 6-inch pipes, each 130 feet long, buried 9 feet deep. His total material cost was $368 at 2014 prices. Before installation, his propane-heated 1,700 square foot farmhouse used about 910 gallons of propane per winter, costing roughly $2,100 at the going rate. First winter after installation, his propane use dropped to 387 gallons. Second winter, 340 gallons. His system has been operating continuously for over a decade, cutting his fuel bill by nearly 2/3 every winter with zero maintenance. Linda Hartman renovated a 1920s farmhouse in central Alberta in 2019. She documented the project in detail on a Canadian prairie homesteading forum. Her installation used a single 140-foot run of 6-inch HDPE pipe buried 10 feet deep. Total material cost was $412 Canadian. Her previous winter heating bill on an electric baseboard system averaged $287 a month. Across a 5-month heating season, about $1,435 a winter. After installation, combined with better weather stripping, her average monthly winter bill dropped to $91 for a seasonal total of roughly $455. Her electrical fan costs about $18 Canadian a year to run. Daniel Kaufman runs a small dairy operation in northern Maine. He installed an earth tube in 2016 specifically to precondition incoming ventilation air for his milking parlor, which by regulation has to exchange air continuously even in winter. His installation was more elaborate, a pair of 180-foot pipes at 11 feet depth, designed to handle a higher flow rate for the barn. Total material cost, including a larger industrial-grade fan, was $1,240. His winter propane use for parlor heating fell from 1,800 gallons a season to 320 gallons. At Maine propane prices, that's a savings of roughly $3,600 per winter. His payback period was under 5 months. The European data layer is worth one more paragraph. Germany's Passive House standard incorporates earth-air heat exchangers as an option for cold climate builds. Data from the Passive House Institute shows winter installations performing within 4% of projected efficiency over installations older than 15 years. The Swedish energy agency Energimyndigheten published a 2018 meta-study of 212 earth tube installations in Scandinavia. The average fuel reduction across all installations was 41% in winter, with systems in rural areas performing better than urban installations due to drier, more consistent soil conditions. Here's a concept worth understanding. In deep cold climates, the system doesn't fully heat the house. It dramatically reduces the workload of whatever your primary heating source is. If your furnace was sized for worst-case winter conditions, it now only has to handle a fraction of that worst case, because the air arriving at the furnace is already 40 to 50 degrees warmer than the outside air. This has 2 secondary benefits most people don't think about. First, your furnace runs shorter cycles, which means less wear on burners, blowers, and heat exchangers. Second, the house experiences fewer thermal swings, because the preheated air dilutes the cold infiltration that normally causes temperature drops in drafty rooms. Your home feels more evenly heated, and your heating system lasts longer. Both wins, no downside. Another way to think about it, without an earth tunnel, your furnace fights a 70-degree temperature differential every minute of a January cold snap. With a properly sized earth tunnel, that differential drops to about 25 to 30 degrees. The physics of heating load scales roughly linearly with temperature difference, so a 30-degree reduction in delta T means roughly a 42% reduction in peak heating load. That's the mechanical engineering reason why real-world installations consistently report fuel reductions in the 50 to 70% range. Fair reasons it isn't everywhere yet. First, condensation is a real issue in winter systems, but in reverse, when cold outside air warms up inside the pipe, moisture in the air can condense on the pipe walls. Good installations include a slope of at least 1 inch per 10 feet of run toward a drain at the lowest point. Without this, water pools inside the pipe, breeds mold, and degrades indoor air quality. Get the slope right, drain the low point. Problem handled. Second, radon. In some soils, particularly granite and certain shale formations, radon gas can accumulate in buried pipes. Before installation, have a soil radon test done. Costs around $60. If radon is present, the system either needs specific venting or shouldn't be built as designed. This is rare, but it matters. Check before you dig. Third, the permitting question. Most jurisdictions treat an earth tunnel as a ventilation modification, which usually requires a simple permit. Some treat it as a heating system modification, which is more involved. Contact your local building department. Search your municipal website for Earth Tube Permit, Earth Air Heat Exchanger, or Geothermal Ventilation Permit. Ask. The answer is usually straightforward. Budget 2 to 6 weeks for approval. This isn't a magic box. It's not going to make your furnace irrelevant in a Minnesota January. What it does is take the worst of the load off the furnace, quietly every minute of every cold day, without asking anything from you beyond the occasional screen cleaning. It buys you independence from a fuel bill that's been climbing faster than wages for 2 decades. It buys you comfort during grid outages, because natural convection will keep moving air through the tube even if the fan stops. It buys you a system that will very likely outlive you. There's one more underappreciated benefit. The preheated air arriving from an earth tunnel is typically drier than cold winter outside air, because the soil absorbs excess moisture along the way. Cold winter air, when rapidly warmed by a furnace, often produces uncomfortably low indoor humidity, causing dry skin, cracked lips, and respiratory irritation. Preconditioned air warms more gradually and retains more of its natural moisture, resulting in more comfortable indoor humidity levels across the winter. Many homeowners report that they no longer need portable humidifiers once an earth tunnel is installed. That's a comfort improvement that's invisible on paper but obvious to anyone who's suffered through a dry, overheated winter home. And there's a preparedness dimension nobody brings up in the brochures. Every year, winter storms knock out power to hundreds of thousands of American and Canadian households. Without power, most modern furnaces stop working. Even gas furnaces require electricity to run their blowers and ignition. An earth tunnel with a small solar-powered fan, or even with natural convection alone, will continue delivering roughly 45-degree air into your home indefinitely. Combined with a wood stove or propane space heater, you have a resilient winter heating system that simply doesn't fail. That kind of redundancy is worth something, even if you can't calculate it in simple payback terms. The knowledge has never been hidden. It's just been underground, literally and figuratively. Conrad Steinberg wrote it down in 1932. Minnesota tested it in 1987. Amish builders have been quietly using similar principles for 2 centuries. The math works. The physics doesn't change. The only variable is whether you decide to act on it. Welcome to the other side of the knowledge gap. It's bigger than you think. Families who know this are sitting warm in January while their fuel bills read double digits instead of quadruple. Start with your soil type. Check your frost line. Measure the distance from your mechanical room to a point in your yard 150 feet away. The rest is just digging. Most homeowners who install these systems describe the same arc of reaction. Skepticism during research. Nervousness during excavation. Mild astonishment the first winter as the furnace runs visibly less than it ever has. Quiet satisfaction every winter after that. The system becomes invisible. You stop thinking about it. You just notice that your propane tank needs refilling half as often. You notice your January bill is laughable compared to your neighbors. You notice, slowly, that you've stepped outside a system that most people have never considered questioning. That shift is the real prize. Not just the dollar savings, though those add up. The deeper change is moving from a passive relationship with your home's energy, where you write checks and hope prices don't spike, to an active one, where physics and geometry and the steady temperature of the earth are working for you silently, year after year, asking for nothing in return. That's insider knowledge. That's the club. The door is open. You just had to know it was there.